Welcome to Lecture 13 for Math 239. This week we'll be talking about recursion in two different senses. In this lecture, we'll be applying recursive ideas to describe sets of strings. Last week, we saw many ways to describe a set of strings using a regular expression S, which is written in terms of the symbols 0, 1, cup, star, etc. Today we'll look at more complicated ways to describe a set of strings, where the symbol that produces the set will occur on both sides of an equation with regular expression-like syntax. Equations like this amount to describing the set recursively in terms of itself. Here is an example. S equals epsilon cup S brackets 0 cup 1. To make sense of this, let's look at the right-hand side. The epsilon, of course, produces the empty string, and then the S0 cup 1 will produce any string produced by S with a 0 or a 1 added to the end. If the S on the right-hand side were some other regular expression t, then all we'd be doing here is defining S in terms of t. But here we're defining S in terms of itself, and we can see the whole equation as a statement about the set of strings produced by S. It says that a string produced by S is either equal to the empty string, or is equal to a string produced by S, followed by a 0 or a 1. Consider now the set of strings that S produces. It must produce the empty string because epsilon appears on the right-hand side. And then if we substitute the empty string into the S on the right-hand side, we see that S must produce the string 0 and the string 1. Substituting either of them in place of the S on the right-hand side, we see that S must also produce 0, 1, 0, 0, 1, 1, and 1, 0. Continuing in this way, we see that S must produce every binary string. In fact, it produces every binary string unambiguously, because every binary string is either empty or is equal to some other binary string with a 0 or a 1 added to the end. We know that unambiguous regular expressions lead to rational functions, and we can apply this idea here except to these equations which contain S on both sides. If f of x is the function that S leads to, then this equation leads to an equation concerning f of x. The left-hand side leads to f of x, and the right-hand side leads to 1 plus f of x times x to the 1 plus x to the 1. This isn't writing f of x as a rational function directly, but it gives an equation that we can solve to find f of x. It's 1 over 1 minus 2x. We know from earlier that that's the generating series for the set of all binary strings, which is what we argued that S produced on the previous slide. The point with these recursive decompositions is that they're capable of describing some sets of strings more simply than regular expressions are by themselves, and they can also describe sets of strings that regular expressions cannot describe. Because of the time constraints that we have in this course, I won't be able to set up the formalism of recursive decompositions with complete mathematical rigor. Instead, I'll focus on showing you how to use these kinds of objects to describe interesting sets of strings, and how to get equations from them that you can solve to find the generating series for these sets of strings. Here is an informal definition of a recursive decomposition. A recursive decomposition of a set pink S describes pink S in terms of itself, using the language of regular expressions, together with the symbol orange S, which produces pink S. Typically, these decompositions can be understood as stating that a string in pink S is either some small particular string, or can be described in terms of one or more smaller strings in pink S. Here's an example. S equals 1 cup 0 S1. Turned into an English sentence, this is saying that a string in pink S is either the string 1, or is a 0 followed by a string in pink S followed by a 1. So pink S contains the string 1, and for any string in pink S, putting a 0 on the front of that string and a 1 on the end gives you another string in pink S. And the equality says that this is the only way to get a string in pink S. It follows that the set pink S is the set that contains all strings consisting of some number of zeros followed by one more than that number of ones. Here's another example. The decomposition S equals 0 cup SS0 is saying that a string in S is either the string 0 or is obtained from two strings sigma 1, sigma 2 in S by gluing them together and adding a 0 to the end. This is a description of a set pink S containing all strings of zeros of odd length. This is true because every positive odd number is either equal to 1 or is the sum of two smaller positive odd numbers and 1. Just like regular expressions, we only really care about recursive decompositions when they're unambiguous. For a recursive decomposition, unambiguous means that each side of the equation produces each string at most once. For instance, the decomposition S equals epsilon cup 1 cup 0 S0 is unambiguous and produces the set pink S, which contains all even length strings of zeros and all odd length strings which are all zeros except for a single one in the middle. This is unambiguous because each string in the set pink S is produced only one way by the left-hand side and only one way by the right-hand side. As a contrast, the decomposition S equals 1 cup 1 1 cup 1 S will produce the set of strings of 1s of positive length. This is ambiguous because the string 1 1 can be produced in two different ways on the right-hand side. You can either produce it as 1 1 itself, or using the expression 1s. If you want two more examples, you might want to go back a slide and convince yourself that the first example from last slide is unambiguous and the second example is ambiguous. In the same way that a regular expression leads to a rational function which is the generating series for the set it produces, a recursive decomposition will lead to an equation that relates rational functions. As an example, look at the decomposition from last slide. S equals epsilon cup 1 cup 0 S0. We do happen to know which set that produces, but that won't be important here. Using the usual rules for which expressions lead to which functions, and also the rule that S leads to the generating series for the set it produces, pink S, we can convert this decomposition into an equation. The equation simplifies to say that phi sub pink S of x is 1 plus x squared times phi sub pink S of x. The context of the equation is that we have a set pink S and we want the generating series for that set. So in this equation, the unknown is phi sub pink S of x. Making that the subject of the equation and simplifying gives that phi sub pink S of x is 1 over 1 minus x. This method works generally to go from an unambiguous recursive decomposition into a generating series. In this case, as a sanity check, we can see that the generating series we got, 1 over 1 minus x, has all its coefficients equal to 1. This is saying that the set S should contain exactly one string of each non-negative integer length. Looking at the definition of S, we can see that this is true. Here's another example where we start with the set pink S rather than starting with the decomposition. We've seen this set of strings before. It's the set of all strings consisting of some number of 1s followed by that number of zeros. Every string in the set pink S is either the empty string or is obtained in exactly one way from another string in pink S by adding a 1 to the front and a 0 to the end. Therefore, S equals epsilon cup 1 S0 is an unambiguous recursive decomposition for the set pink S. This leads to an equation where both sides are rational functions involving the generating series for pink S. We can solve this equation to get that phi sub pink S of x is 1 over 1 minus x squared. As a side note, even though the set pink S being described here is rather simple, I mentioned last week that this is actually a set of strings which is not a rational language. There is no regular expression that produces the set pink S. Since we just used this method to find the generating series for this set, this shows us that recursive decompositions are a more powerful problem-solving tool than just regular expressions are. Even with this more powerful tool, there are still some sets of strings that are difficult to describe. An example is the set of strings that avoid a particular substring, like 11100. Unlike the previous few examples, it's not particularly easy to describe a string in the set pink S in terms of smaller strings in the set pink S. Any procedure you can think of for going from smaller strings to bigger strings will either potentially introduce a 11100 where you don't want one, or it will fail to produce some of the strings that don't have 11100. The best way to solve this problem is actually to introduce a different, related set of strings. Let pink T be the set of all strings that have exactly one occurrence of 11100, and where that occurrence occurs in the last 5 bits. Note that the sets pink S and pink T are disjoint, and that if you add a 0 or a 1 to the end of a string in pink S, you might have another string in pink S, but you also might have a string in pink T. The idea is to not write down a single unambiguous recursive decomposition that describes S, but instead to write a pair of unambiguous recursive decompositions that both describe S and T. I emphasize the word idea. Introducing this set is not simply something obvious or a matter of following your nose. It's an example of mathematical creativity. Here are the two sets S and T, and here is the pair of recursive decompositions that describe both S and T. These decompositions relate S and T in two different ways. The first one, in plain English, says that every string in S union T is either the empty string, or it can be obtained in exactly one way by appending a 0 or a 1 to a string in S. If you look at the definitions of pink S and pink T, you'll see why this is true. If I take a string without 11100 as a substring, and I append a 0 or a 1 to it, then perhaps I still don't have 11100 as a substring, or perhaps I do, but if I do, it will be in the last 5 bits. Since the cups here all correspond to disjoint unions, and no string can be produced in two different ways by the left-hand side, this is an unambiguous decomposition. The second decomposition is simpler. It simply says S11100 equals T. In English, this is saying that each string in pink T is uniquely obtainable by taking a string in pink S and adding a 11100 to the end. Moreover, if you take a string in pink S and add a 11100 to the end, you're guaranteed to have a string in pink T. This last point is slightly subtle. If I add 11100 to the end of a string that does not contain 11100, I will have only introduced one new copy of 11100, and it will be at the very end. If I was doing this with another string, like 10101, then it would be possible to take a string that does not contain 10101, to add a copy of 10101 to the end, and obtain a string that contains 3 copies of 10101. Now we have two unambiguous recursive decompositions that describe S and T, and we're going to take both of them, turn them into equations, and solve them. Applying the exact same rules as last time, but this time to both of these equations, we can simplify to get two equations that describe the generating series for S and T in terms of rational functions. We're going to solve these equations to figure out phi S and phi T, so we have two simultaneous equations in two unknowns. In this case, it's easy to solve them by substituting the second equation into the first. And we end up with phi sub S of x is 1 over 1 minus 2x plus x to the 5. We could solve for phi sub t of x if we wanted, but there's no point. T was just a set we introduced to make the problem easier. It wasn't the generating series we cared about. I might sound like a broken record here, but I want to reiterate that what the algebra is doing is nothing short of incredible. Phi s and phi t are both power series with infinitely many coefficients, and each coefficient tells you the answer to a counting problem. We solved these equations here for phi s and phi t, not caring about the combinatorics, and somehow the algebra gave us the right answer for every coefficient at once with minimal effort. In this last example, we introduced a new set to help us. It turns out that sometimes you need more than one new set. Here's a quick example where you do. Let pink S be the set of strings not containing 101 as a substring. The two new sets that we need, pink T1 and pink T2, are shown here. Pink T1 is the set of strings whose only occurrence of 101 is in the last 3 bits. Pink T2 is the set of strings that have two occurrences of 101, both occurring in the last 5 bits. All the strings in Pink T2 will end in 10101. You may be wondering why we need 2 new sets here, where we didn't in the last example. The answer to that really comes from fully understanding what's on the next slide, but I can tell you in brief what property of the string causes this. The property that the string 101 has, that the string 11100 from last example doesn't have, is that you can shift 101 to the left and it will overlap itself. Again, it doesn't need to be obvious to you that this shifting property has anything to do with what we're talking about. But if you think carefully about what's going to be happening on the next slide, the relationship should be clearer. Here are the 3 recursive decompositions that relate these 3 sets. I'll leave it to you to verify that they actually describe these 3 sets and that they're unambiguous. Here is the working for how you turn these 3 relationships into equations and then solve them to find the generating series for S. Like the last example, the easiest way to solve these equations is just substitution repeatedly. In summary, an unambiguous recursive decomposition uses the language of regular expressions to describe a set of strings in terms of itself. By the same ideas as last week, such a decomposition will lead to an equation that can be solved to find the generating series for the set. Sometimes the easiest way to describe a set recursively is in terms of one or more other sets. This includes many examples where the set of strings is defined by excluding a particular substring. These examples are discussed in more generality in the course notes. Thank you for watching.